So I have two blocks on a floor with a coefficient of 0.2 between the blocks. A 1 kilogram block and a 4 kilogram block. And there's a spring. So I compress the spring by 20 centimeters. So I'll put down 0.2 meters equals delta x. Right? So spring gets compressed, and I put the 1 kilogram block there. And then it skids a total distance of 180 centimeters or 1.8 meters until it hits this 4 kilogram block. And so we can draw the next picture is with the spring relaxed again. And this 1 kilogram block is moving at some speed, let's call it v1, in that direction, and it hits this guy. And then ultimately, after it hits, we can move into the future, and I don't need to write all this again. We've got our 1 kilogram block and our 4 kilogram block moving along at some speed, v final. There's a force of friction here in this direction on that 1 kilogram block. So I can think of, maybe using a dynamics lens, but I'm going to say, look, what if I use an energy lens? If I use an energy lens, as soon as I say energy lens, I need to support that statement with an energy conversion. And I can say, yeah, there are very clear energy conversions here. I start with the spring potential energy, and that turns into kinetic energy of the 1 kilogram block, which turns into some more kinetic energy of the 1 kilogram block, but some heat is given off in the process, right, of the friction. And that ultimately turns to some kinetic energy of, let's call this 5 kilograms, because they stick together, of the 5 kilograms, plus this heat of friction, plus the heat given off, because this is an inelastic collision. So we're going to say inelastic. And so it seems as though, yes, I should be able to use an energy lens. I can find this, and I can find this. So I can calculate the kinetic energy of this guy before they hit. I don't know this. So an energy lens is not going to get me to the very end. It'll only get me to this final speed. But then when I have a collision, I know I conserve momentum because there's no outside forces. So I can go forward and try to calculate this. This is 1/2 kx squared. And this turns into the kinetic energy of the 1 kilogram mass. That'd be 1/2 m of the 1 kilogram v1 squared. And this heat given off is the work done by friction. So this is work of friction, which is force of friction times delta x, where friction is acting. So let's go over here. How can we find the force of friction? Oh, I know. Force of friction is equal to mu times the normal force. And we can look, we have to use a dynamics lens now because we're looking at forces and acceleration equals 0 in the y direction. So I'm going to use dynamics. And I can say, yeah, sure, the force of gravity and the normal force. And because there's no acceleration in this direction, the vector sum of the forces is mass times acceleration in the y direction. The y direction is equal to 0. The normal force must equal the force of gravity, must equal mg. So the force of friction is equal to mu times n, which is equal to mu times mg. So I can write that in, mu times mg. And now I ask myself, should this be positive or negative? And there's two ways to look at this. One, this is your original energy, and this is your final energy. That heat given off is positive heat. If we had said initial energy plus work, that would be negative because it's negative work on the system. But another way to look at it is this frictional heat going to make my final kinetic energy bigger or smaller? This stays the same. So the bigger this number is, the smaller this one is. So this should be positive. So I'm good. because I know the heat given off and the original spring potential energy, I can solve this to give me V1. And if I want to, I can solve it and say this is the square root of 2 times the kinetic energy over the mass, if I want to. Now when this guy hits, I need to say I'm going to use a momentum lens, because I know that delta P is equal to 0 of the system, because outside forces equals 0, or the sum of the outside forces equals 0. There's no outside force acting on it. And so I can say M1 V1, the momentum that this guy has, is equal to the final momentum of the system, which is m of the system times velocity final. That's just equal to 5 kg. And that information should be enough to solve for the final velocity.